Welcome, curious minds, to another deep dive. Imagine trying to understand this vast, intricate machine, but all its parts seem to operate on completely different principles, like no clear connection at all.
Right, a real puzzle.
Exactly. That's a bit like the world of particle physics back in the mid-20th century. Today, we're plunging into that fascinating world, guided by the insights of a true visionary who helped, piece that machine together. Nobel laureate Sheldon Glashow.
A real giant in the field.
Absolutely. Our mission for this deep dive is, first, to explore Glashow's own remarkable journey, how a curious kid grew into, well, a titan of theoretical physics. Then we'll unravel the threads of his profound 1979 Nobel Lecture towards a unified theory threads in a tapestry. We'll see how his personal story intertwines with the grand scientific quest to understand the universe's most fundamental forces, and what vital lessons he shared with a new generation of physicists.
And what's really fascinating here is how Glashow's personal path kind of mirrors the evolution of physics itself. From a fragmented understanding, a patchwork quilt, as he put it,
Yeah, I love that metaphor.
to a much more coherent, beautiful picture, a tapestry. You'll discover how early curiosities and, well, seemingly small decisions can lead to these groundbreaking, unifying discoveries.
So where did this intellectual curiosity, this drive, begin for him? What were the early influences that shaped the remarkable mind of Sheldon Glashow?
Well, Glashow's story starts with his parents, Louis Glashow and Bella Rubin. They immigrated in New York City from Bobrusk, Russia, basically seeking freedom and opportunity denied to Jews there.
Right.
His father became a successful plumber, and, though his parents didn't go to university themselves, they were absolutely adamant their children would. Glashow always emphasized how he was taught the joys of knowledge and of work well done. That really set the stage.
It sounds like he was immersed in a home environment that really valued education and, well, hard work. How did that translate into his specific, almost precocious interest in science?
Yeah, he knew he'd be a scientist from a really early age. He credits his older brother, Samuel, who sparked his interest in the laws of falling bodies. Get this, when Glashow was just 10.
10 years old. Wow.
I know. His father even helped equip a basement chemistry lab where, at 15, he became skilled in synthesizing dangerous selenium halides.
Dangerous chemistry.
He humorously notes that's a path he never repeated, but, clearly shows that early, hands-on, maybe even slightly mischievous curiosity. That was his style.
An early start with dangerous chemistry indeed. It paints a picture of a fearless, hands-on learner. But he wasn't alone in his passion, right? What about his peers in education? Did that collaborative spirit emerge early?
Oh, absolutely. He went to the Bronx High School of Science, which was like a real incubator for scientific talent back then.
A legendary school.
Totally. And there, he and his classmates really spurred each other on to learn physics. They did it while commuting on the New York subway, people like Gary Feinberg and, yes, even Steven Weinberg.
The Weinberg, his future Nobel laureate.
The very same. And another classmate, Dan Greenberger, even taught him calculus in the school lunchroom because high school math at the time just ended with solid geometry.
In the lunchroom. That's amazing.
Right. This early, intense peer collaboration continued at Cornell and Harvard. And he makes a point of saying he learned as much from my peers as from my teachers. That collaborative spirit was just fundamental for him.
Sounds like a dream team of future physicists. He eventually lands at Harvard for grad school, working with a giant in the field, Julian Schwinger. What was that mentorship like? Was it straightforward?
Well, his supervisor, Schwinger, had about a dozen doctoral students at a time. So Glashow said it was difficult, but also rewarding to actually get his ear.
I can imagine.
Glashow's 1958 thesis, The Vector Mason in Elementary Particle Decays, already showed his early commitment to a unified electroweak theory. But here's a funny story. There's this anecdote that he and Schwinger were supposed to write a paper summarizing their thoughts on weak electromagnetic unification.
Okay.
But one of them apparently lost the first draft to the manuscript, and that was that.
No way. A lost Nobel-level manuscript. That's, talk about a truly human moment in scientific history.
Right. It makes you wonder how many other pivotal ideas might have been just, lost to history through sheer human error.
What does that tell us about the often messy reality of scientific progress,
It's a fantastic illustration of, well, serendipity.
Yeah.
And maybe the less glamorous side of groundbreaking work. I mean, it seems like a missed opportunity, but sometimes those detours or even setbacks force you down a different path, one that's ultimately more fruitful.
That makes sense.
And for Glashow, his path certainly continued.
So where did he go after Harvard? Did these detours keep shaping his work?
He initially planned to work at the Lebedev Institute in Moscow with ITAM, but he ended up in Copenhagen at the Niels Bohr Institute, and then CERN from 1958 to 1960, basically waiting for a Russian visa that never materialized.
So the Moscow plan fell through.
Yeah, but he reflects that perhaps all was for the best,
Mm-hmm.
because it was during those years in Europe that he discovered the SU2-XU1 structure of the electroweak theory that was absolutely central to his Nobel-winning work.
Wow, so the detour was crucial.
Incredibly crucial. He came back to Harvard in 1966 and stayed there, eventually becoming the Eugene Higgins Professor of Physics. It really shows how those unplanned moments can be pivotal.
Absolutely fascinating. And he also made some significant predictions with collaborators later on that really solidified his work, didn't he?
Oh, definitely, particularly in 1969, working with John Eliopoulos and Luciano Maiani. They found the arguments that predicted the existence of charmed hadrons, basically, a new type of particle containing what we now call a charm quark.
Okay, the charm quark.
Then, in early 1974, with Alvaro de Ruula, or Howard Georgi, they predicted charm would be discovered, either in neutrino physics or in electron-positron annihilation experiments.
So they pinpointed where to look.
Exactly.
Yeah.
And this was validated just months later with the discovery of the J-psi particle. He recalls realizing many diverse strands of research were converging on a single theory of physics. It must have been an electrifying moment.
I bet.
He even joked with Howard Georgi that if quantum chromodynamics, QCD, was any good, it should explain the specific mass difference between two particles, sigma and lambda. And Georgi apparently showed him it did the very next day.
The next day. That's incredible speed.
Right. That rapid validation must have been incredibly exciting.
So he's this world-renowned scientist, but what I found particularly fascinating from his biography was his approach to teaching. Despite all the complex theory, he didn't just teach future physicists, did he?
No, quite the opposite. He was actually honored to participate in the Harvard Core curriculum program. He taught a course called From Alchemy to Quarks.
From Alchemy to Quarks, love that title.
Yeah. And his students, as he notes, are not and will never be scientists.
Yeah.
Yet he found them just as fascinated as I am by the strange story of the search for the ultimate constituents of matter.
That's wonderful.
Really highlights his deep joy in discovery and, sharing that knowledge, not just with experts, but with anyone curious enough to listen. It's like he believes science is a story for everyone.
That's a perfect segue into the heart of our deep dive. We've journeyed through the remarkable life that shaped him. Now let's connect that personal story to the grand scientific tapestry he helped weave, specifically his iconic 1979 Nobel Lecture towards a unified theory threads in a tapestry. He specifically prepared this lecture for physics students, right?
That's right.
So what was the landscape of elementary particle physics like when he first started his career, say, back in the mid-1950s? And how had it changed by the time he gave this lecture?
Okay, so we connect this to the bigger picture. Glashow vividly describes the study of elemental particles in 1956, when he really began his theoretical physics journey as a patchwork quilt. Patchwork quilt. Yeah. Electrodynamics, weak interactions, strong interactions. They were all entirely separate disciplines. Each had its own set of rules, its own phenomena. There was just no coherent theory connecting them all.
They're like different puzzle boxes.
Exactly. You had concepts like parity violation, the successes of QED, hadron resonances, strangeness.
Yeah.
All well-defined parts of the picture, but they could not be easily fitted together. It was a really fragmented view of the universe.
So lots of pieces, but no unifying picture. And what happened by the time he delivered this lecture in 1979, just over 2 decades later?
Well, by 1979, he states, they had what's called a standard theory of elementary particle physics. And in this theory, strong, weak, and electromagnetic interactions all arise from a local symmetry principle.
A unified principle.
Yes, he calls it a complete and apparently correct theory. It provided qualitative descriptions, precise quantitative predictions, and crucially, had no experimental contradictions at the time. It transformed from that jumble of ideas into an integral work of art. The patchwork quilt has become a tapestry.
That tapestry metaphor is just so powerful, isn't it? And he emphasizes that it wasn't the work of one genius, but a collective effort.
Exactly. He really stresses that tapestries are made by many artisans working together. The unification of weak and electromagnetic interactions, the prediction of neutral currents, which was part of his Nobel Prize, that was just one thread.
Okay.
Other crucial parts included the evolution of the quark hypothesis and quantum chromodynamics, QCD, which describes the strong force. All of them are woven together in the tapestry. One part makes little sense without the other. He underlines that even the electroweak theory itself wasn't some singular flash of insight, but the result of the collective endeavor of many scientists, both experimenters and theorists. A real testament to collaboration.
Let's rewind a bit then to the old threads of his research. Even before his major work, what were some of the early ideas floating around about unifying these fundamental forces?
Well, back in the 1920s, only gravity and electromagnetism were really known as fundamental forces. Then the strong and weak forces were discovered. And in the 1930s, Yukawa wondered if there was an analogy between them. He proposed that maybe all forces result from meson exchange mesons being these particles that carry the force. Glashow calls this the first attempt to unify strong and weak interactions, but notes it was fully 40 years premature. He even points out that Yukawa could have predicted neutral currents back then, because Yukawa's neutral meson, needed for nuclear force properties, was also weakly coupled to lepton pairs.
40 years premature, wow.
Yeah, and a key concept that emerged later was this idea of a gauge principle. Imagine a theory where you can make local adjustments to your perspective, say rotating the internal properties of particles at every point in space and time, but the actual physics, the stuff you measure, stays the same.
Okay, so the outcomes don't change.
Right, that consistency is the gauge principle. And it's a really powerful tool for building theories, especially for forces like electromagnetism. This was generalized in 1954 to apply to more complex symmetry groups. But this raised a big question.
What was that?
If all the force-carrying particles, the gauge mesons, must be massless according to these gauge theories, and we only knew the photon was massless,
Yeah.
how do the other force carriers, like for the weak force, get their mass?
Right, because the weak force carriers are massive.
Exactly. And Glashow notes there was no good answer to this question until the work of Weinberg and Salam, and of Gross, Wilczek, and Politzer. Until then, masses were just put in ad hoc, basically added manually without a solid theoretical reason. That was a huge barrier.
So the path was definitely not clear. What was his own specific contribution in that early fragmented era, trying to connect these pieces?
Well, Glashow recounts that his Harvard thesis in 1958 under Schwinger really pursued this belief in a unified electroweak gauge theory. He actually wrote, "It is of little value to have a potentially renormalizable theory of beta processes without the possibility of a renormalizable electrodynamics. We should care to suggest that a fully acceptable theory may only be achieved if they are treated together."
So he was pushing for unification early on?
Absolutely. He used the original SU2 gauge interaction of Yang and Mills, but he quickly realized this first attempt was, in his words, ugly and experimentally false, mainly because it didn't incorporate neutral currents, which we now know definitely exist.
Okay, that's a crucial point. His 1960 work in Copenhagen on the SU2S structure, that was pivotal, right? But what was still missing from that framework, even though it was groundbreaking?
Right. That work, which was done independently by Salam and Ward as well, saw that you needed a bigger gauge group than just SU2 to unify these forces. Glashow was led to the group SU2-XU1, partly by analogy with how strong interactions were being thought about. Now, this model correctly predicted two electrically neutral force carriers, the familiar massless photon and a massive neutral vector meson. He called it B back then, but today we know it as the Z boson.
The Z boson, right?
The form of the neutral current interaction it predicted was later verified experimentally. But two big things were missing. First, its strength wasn't actually prescribed by the theory. And second, and this was crucial, the model was not, in fact, renormalizable.
Ah, that word again, renormalizable.
Yes. These glaring omissions, as he called them, were to be rectified by the work of Salam and Weinberg and the subsequent proof of renormalizability.
So let's unpack that. Renormalizability. Why was it so important, and how did Glashow's own pursuit of it lead him to this surprising, almost ironic conclusion about his own earlier work?
Renormalizability is just essential. Without it, when physicists try to calculate particle interactions at very high energies or, with high precision, their equations would just blow up. They'd get infinite, meaningless answers.
Not very useful.
Not at all. It's like a recipe that works fine for a small batch, but if you try to scale it up, the ingredients just vanish or explode into nonsense. A renormalizable theory, though, gives you consistent, finite, testable predictions, no matter how extreme the conditions.
Got it. Makes sense.
Glashow worked really hard on this. He even wrote what he calls a notorious paper in 1959, where he alleged that a softly broken gauge theory, where symmetry breaking came from just putting in mass terms explicitly, was renormalizable. He quickly found out that was false.
So a dead end there.
Pretty much.
Mm-hmm.
Later, in 1970, with Iliopoulos, they did manage to show that a wide class of these infinities or divergences would cancel out nicely. But they still left some mere divergences remaining. They proved this difficult theorem showing some divergences were reduced, but ultimately their efforts were in vain for the bigger problem. Then came the big revelation in 1971.
Okay, so what was this missed boat moment he talks about regarding renormalizability? How did that hit him?
Well, in the spring of 1971, Glashow was informed that a student of Veltman's, a young physicist named Gerhard Tooft, had established the renormalizability of spontaneously broken gauge theory.
Spontaneously broken. What's the difference?
The key idea, which came from earlier work by Goldstone, Higgs, and Kibble back in '64, was that the underlying gauge symmetry is exact but hidden. Particles get mass through a mechanism, the Higgs mechanism, not by just forcing mass terms into the theory by hand, which breaks the symmetry explicitly.
Ah, okay. A more subtle way.
Exactly.
Mhm.
And Glashow reflects, I had worked diligently, but I completely missed the boat. He'd even had many conversations with Goldstone and Higgs in 1960 and wonders, did I neglect to tell them about my SU2-QU1 model, or did they simply forget?
Wow, that's quite a reflection.
It really is. This missed boat moment is incredibly telling. It shows how even brilliant minds on the right track can be so focused on one approach that they miss a crucial alternative solution, especially if it comes from a slightly different conceptual angle.
A lesson in scientific humility.
Definitely. And the iterative nature of discovery. It was actually Salam and Weinberg, who had more experience in formal field theory and had both worked with Goldstone, who finally used this key insight about spontaneous symmetry breaking. That led to the successful, renormalizable Weinberg-Salam theory.
That's a perfect example of how science can be this complex, winding road, even for the brightest minds. Okay, let's tackle another stubborn problem. The strangeness-changing neutral current. This sounded like it was a major headache for a while.
It really was. And it raises an important question. Why did Glashow kind of abandon his electroweak theory for a bit between 1961 and 1970? One reason was that failed attempt at renormalizability we just talked about.
Right.
Another was the huge empirical success of the SU3 symmetry scheme for strong interactions. He felt there just wasn't room enough for commuting structures of weak and strong currents if both were based on gauge theories, especially since strong interactions seemed so dominant then.
Okay, so SU3 success kind of overshadowed things.
Yeah, and the core problem came from his 1960 model for hadrons particles made of quarks. In that model, the charged current, which causes changes in this property called strangeness, would logically force the neutral current to also change strangeness.
But experiments showed that didn't happen.
Exactly. It was well known experimentally that strangeness-changing neutral currents were either strongly suppressed or completely absent. So his model didn't match reality, his solution at the time. He ended up suppressing all neutral currents. The baby was lost with the bathwater. He threw out the good idea, neutral currents, to get rid of the bad prediction, strangeness-changing ones.
Oof. Not ideal. So what was the missing piece? The aha moment that finally cracked this puzzle?
Well, in 1961, Glashow and Gell-Mann confirmed this problem existed, concluding something essential was missing. The solution finally emerged from the quark hypothesis. In 1964, during a brief return to Copenhagen, Bjorken and Glashow and others too suggested extending the known three-quark system, up, down, strange, to four quarks. They introduced the charmed quark.
They're charmed quark again.
Right. Their motivation included enforcing an analogy between the weak currents of leptons, like electrons and neutrinos, and hadrons, like protons and neutrons. Since there were two known pairs, or doublets, of leptons, they figured there had to be two doublets of quarks as well.
So hold on. Are you saying they essentially stumbled upon the mechanism that would later be called the GIM mechanism for Glashow, Iliopoulos, Majani way back then, but didn't realize its full significance?
Yes, that's precisely it. The weak current that Bjorken and Glashow introduced in '64 was precisely the GIM current. And crucially, its associated neutral current conserves strangeness. It didn't change it. That was the key.
So it solved the problem.
It would have solved the problem if they'd inserted it back into their earlier SU2 electroweak theory. But Glashow notes, I had apparently quite forgotten my earlier ideas of electroweak synthesis. The problem which was explicitly posed in 1961 was solved in principle in 1964. No one, least of all me, knew it.
Unbelievable. Why not?
He wonders if maybe they were befuddled by the chimera of relativistic SU6. At the time, another trendy but ultimately less fruitful theoretical idea that was popular then. It just shows how easily even brilliant people can get distracted.
Incredible. So When did the connection finally become clear? When did these threads come together into that unified tapestry?
It actually took another 5 years. In 1969, Glashow, Iliopoulos, and Maiani returned to this question of strangeness-changing neutral currents. Glashow even says it was incredible that the problem was totally ignored for so long.
Hmm.
They showed how the unwanted effects, these strangeness-changing neutral currents, would be completely eliminated if you had this conjectured fourth quark, the charm quark. Now, this work was done 3 years after Weinberg and Salam published their epical work on the electroweak theory.
And they didn't connect the two initially.
Apparently not. The relevance became evident only a year later, Glashow says, when Hooft and others proved that the Weinberg-Salam framework was renormalizable. Then, suddenly, everything clicked. With the GIM mechanism incorporated, the theory was trivially extended from a model of leptons to a complete theory of weak interactions, including hadrons.
And then it was up to the experimenters.
Exactly. The ball was then squarely in the hands of the experimenters. And that led, fairly quickly, to the discovery of charmed hadrons and the conformation of neutral currents with exactly the properties the theory predicted. It's a fantastic example of how these different lines of research can just unexpectedly converge.
So by 1979, the standard theory was largely in place, a unified tapestry, as he called it. But Glashow's lecture wasn't just a history lesson, it bravely looked to the future. What did he predict about experimental physics? Especially this shift he mentioned from accelerators to mines.
Right. He observes that while earlier discoveries, like pions and strange particles, came from just observing cosmic rays passively.
Like just waiting for nature to show you something.
Exactly. But the 3 decades before 1979 heavily relied on active experiments using these enormous particle accelerators. He suggested we might see a rebirth of passive experimentation, driven now by theoretical ideas from particle physics and astrophysics. He thought the concentration of all high-energy physics at just a few big accelerator labs may be a thing of the past. Think about things like large underground detectors searching for rare events, like proton decay or neutrinos.
Does that mean he thought accelerators were becoming obsolete?
Oh, not at all. He really emphasizes that accelerators remain an essential, if not exclusive, tool. He points out that the existence of the zero particle, predicted to be around 100 G, was a crucial but still quite untested prediction of the electroweak theory back then. New machines like LEAP at CERN and Isabel in the U.S. were mandatory, he said, for making further dramatic discoveries.
And not always things theorists predicted, right?
Right. He noted that future discoveries wouldn't always have been predicted in advance, highlighting the vital role of pure experimental exploration. You need both theory-guiding experiment and experiments pushing the boundaries.
Okay, so looking beyond the breakthroughs he was part of, where did Glashow see the next big frontier in theoretical physics? What was the next step beyond the standard model?
Glashow says we must believe in the ultimate synthesis of strong, weak, and electromagnetic interactions into what's called a grand unified theory, or GUT.
Grand unified theory.
Okay, he points to his own SU5 theory, developed with Howard Georgi as one example. These GUTs put the known forces into an even larger, simpler underlying gauge group. But this concept has a truly profound, almost shocking implication.
Which is?
It implies that the proton, and indeed all nuclear matter, must be inherently unstable.
Wait, protons decay? That sounds completely radical. Everything we know is built on protons being stable.
It was considered mad when he first discussed it back in 1974. But by 1979, sensitive searches for proton decay were actually being launched. Theoretical estimates suggested a lifetime may be shorter than 10 to the power of 32 years.
Which is an unimaginably long time.
Astronomically long, yes, but still finite. He predicted that if proton decay was discovered, it would be like the heroic days of the discovery of the nature of beta decay all over again. It would be revolutionary.
That really makes you think.
It raises a big question for you, our listener. Imagine a universe where all matter is inherently unstable, even if it takes trillions upon trillions of years to decay. How does that fundamentally change our perception of stability, of permanence, of the ultimate fate of everything?
That's a mind-bending thought. It totally reframes how you think about existence. He also touches on what he calls premature orthodoxy. What was his skepticism about the accepted models of his time?
Right. So the discovery of the JP-psi particle in 1974 seemed to reinforce the idea of just 4 quarks and 4 leptons. But then very quickly after came classic surprises. The tau lepton and the B quark were discovered.
Unexpected additions.
Totally unexpected. This quickly led to a new fashionable concept, these families or generations of fundamental particles. Since they now had the tau and the B, this model predicted a third partner quark for the B, a quark with charge plus 23, which they call the T quark, or top quark. This three-family structure became the basis for a vast and daring theoretical endeavor.
But Glashow wasn't fully convinced.
No. He expressed little faith in this new orthodoxy. Why? Because as of 1979, the predicted top quark hadn't been found. And the particle made of a top and antitop quark, the toponium analogous to the J psi or upsilon, would have to be much heavier than expected based on the pattern, heavier than 30 g he estimated, compared to the upsilon's mass of less than 10 g.
So the pattern seemed broken.
It looked potentially broken. He and Howard Georgi were actually working on unorthodox models without a top quark. These models suggested exciting alternative experimental possibilities, like maybe new SU2 gauge interactions that could explain how the B quark decays and also explain CP violation, this subtle asymmetry in physics laws. He even speculated about a possible second zero boson and other bizarre decay schemes for B matter.
So his skepticism wasn't just being contrarian, it was rooted in observation and led to near-theoretical ideas.
Exactly. His core point was crucial, and it's a timeless lesson in science. It is too early to convince ourselves that we know the future of particle physics. There are too many points at which the conventional picture may be wrong or incomplete. Say the established standard model, the SU3 XSU2YU1 gauge theory with three families, not as the final answer, but as a good beginning, not to accept, but to attack, extend, and exploit. We are far from the end.
Not to accept, but to attack, extend, and exploit. That powerful.
It's a powerful call to arms for scientists, really. A reminder that even our most successful theories are probably just way stations, not final destinations.
What an incredible journey through the mind of Sheldon Glashow. I mean, from a curious kid in a basement lab tinkering with chemicals.
Dangerous chemicals?
Right, to a Nobel laureate helping stitch together this amazing tapestry of particle physics and teaching us so much about how science actually gets done along the way.
His story is just such a powerful reminder that science is rarely, if ever, a straight path. It's messy. It's filled with forgotten ideas, unexpected detours, absolutely crucial collaborative efforts, and maybe most importantly, that constant essential questioning of even the most established dogmas.
Yeah, the idea that even a Nobel Prize-winning theory like his is just a way station, as you said, on a much longer journey. Or that the proton itself, the bedrock of matter, might one day just decay. It really expands your perception of what's possible, doesn't it?
It really does. It prompts us to consider that our current understanding of the universe, no matter how complete it might seem right now, always leaves room for the truly unexpected. For those hidden threads, just waiting for someone to find them and start weaving again.
So for you, our curious listener, here's a final thought to chew on. What patchwork quilt in your own field, or maybe just an area of interest you follow, might be waiting for someone to find those unifying threads? To weave it into a beautiful, coherent tapestry? And maybe what's the premature orthodoxy of today that might be vigorously questioned, attacked, and perhaps completely rewritten tomorrow?
Food for thought.
Definitely. Thank you for diving deep with us today. We'll be back soon with another fascinating exploration.